Greetings everyone, I am Christian here to explain a paper on Kronecker product.
Something like neural networks, you'll see what is a neural network, basically how it functions. So neural network since consists of an input layer which is given images or something, we need to classify them and give us an output. In between we have something called summation. So this summation, what we will do is addition of all the weights, and we have particular value that will propagate to the next value. The number of hidden values, hidden layers will be correspondingly saying how the function good is. How with these function A, we try to determine what is the output. So in this sigma and all will be based on the partial derivative what we learned. Like this function will be like in that sum. So you could see here how the weights initially go to the sigma and like come back to again. That is the error correction actually. So for that only we have methods such as the least squares method to minimize that corresponding optimization error. So we will now see how we can use Kronecker product for a better better optimization compared to other algorithms. So so what's our goal is that to reduce. See, we have an input data with input and target. So we are given the input and output. So we need to train the neural network to detect the test data set. So what we try to reduce in the sense we try to reduce the error. So this is nothing but the error function. So in that case, when we try to go about in this way, what we observe in the sense, what are the then coming, how we reduce the error in the sense, we have methods such as least squares or else we go with the stochastic gradient method. This is very famous method in stochastic gradient, which will be generally used. Like the here how this delta theta means the change in the weight. This how the weight will be changed will be the with respect to the function. This is nothing but the partial derivatives. This is how in stochastic gradient the factor will change. The how the weight will update itself in the sense that will be a function of theta minus of this factor. This factor is nothing but I told about the partial derivatives. So this will be based on that factor. This is called the stochastic gradient method. This is first order method. Speaking about second order method, we have Gauss method. So compared to as of now, what's the problem in the sense people will prefer just the first order method because the stochastic gradient. Though first order methods are not so so good enough to explain the questions, which question is what in the sense. So because of it, the first order method will have less accuracy than second order. But second order, if you see the space of it is too high. So this is the matrix of second order, how G inverse space. When this G inverse space, in order to compress and do the function, it takes lot of time enough. So that factor will be like that. Because of this only factor, people never prefer Gauss Newton method or second order method. So they came up with an alternative such as diagonalization matrix. What if we take the diagonal elements alone? What will be the resultant there? Then they tried with that. Then they tried to take only the. Then they tried to observe what will be the change if we take the second order method. So up to this we have said about this. So then even more since it is a very big order, we try to do SVD operation. So we decompose the matrix into three halves like USV matrix. Where USV matrix corresponds with where a singularity matrix will be this matrix. So since we know we are just shifting to the other side U into inverse and since we know all eigenvalues and eigenvector matrix are orthogonal, S is the singularity matrix. We have an expression for singularity matrix as this. So up to this we try to decompose the matrix and see the results. So what we observe in the sense we observe this. What we observe in the sense the reality matrix when we do the second order versus the eigenvalue, what we observe they vary high much. That because of the diagonalization, the amount of the vary is too much. It's not they're not matching. The variance of them is not matching because when we do this singularity is not proven enough to make the things well. So, for example, if you observe this is the first. The green is the original one. The Fisher matrix is nothing but it contains of variance matrices. So the second method was what I told as diagonal matrix. You could see how much it is varying. Like this should be the actual one, but when we take the SVD decomposition in the second order method, this is how it becomes. It is far it is varying from the original one. So that's what our Kronecker product comes to the place. So what we observe in the sense how Kronecker product is a good in a sense. Here why they took diagonal in the sense because they felt diagonal elements will have all the data. Because of this reason, they felt like okay, diagonal matrix will be fine. But what they observed was like it is not the case. So when they went for Kronecker product, we know about the Kronecker product is like everywhere in the Kronecker product will be like much of Kronecker product is sparse matrix. In that case, what happens in a sense like only the diagonal matrix is much concerned about it. Like every element will be in the Kronecker product will be over the diagonal. So this was evident. Like we could see again this was good enough than compared to the previous method. We took it off. Again we did the eigen decomposition saw. But what we observed in the sense, this is nothing but the property. How this is nothing but the property how we did U will become UA into UB will become that matrix. SA into SP will become. But here also the singularity matrix is not equal to what is expected. Here we expected some value, but this value is far greater. But we do here the same method, but this is not equal to this process. So here also again a problem we face is that this singularity matrix is not that we could not appreciate it. We wanted to improve this also. So again we got a method like what if we do see this is the final matrix what we got in decomposition is SA and SP which is not approximately equal to that. So what we finally did in a sense we took a when we went a method eigenvalue characterized Kronecker product EKFAC. So in this method what we do in a sense we do the same Kronecker product, but here the S matrix is we directly take the what was the initial matrix. We here we felt this is not equal to that matrix only, right? So what we do in a sense, we, instead of taking we keeping singularity matrix there, we directly substitute with this result. So what were the results if we consider? So we spoke about the Fisher matrix, variance matrix, diagonal is varying too much. But if you see without that KFSC is slightly varying. It's going out of box of the Fisher matrix, so it's too extending too much than the Fisher. That was a problem which we faced. When you go for eigenvalue based, it controls over the variance is much controlled how the extension is there. The scalability is too conserved here. So that was about the different method. What is the exact application we use? So when we test across two data sets. So for example, I'll show the further slides. I'll explain our data set. Like we'll explain the test data set. But before that, we'll see how like eigenvalue with eigen without eigen how it varies. You could see if this is nothing but the error approximation. You could see when we use eigenvalue, the error is too minimal. So in that case, this is the thing we see. We could see how the basis vector or how it differs because since we know in Kronecker product one only the diagonal element will have the space. So with respect to we could see only the diagonally the data is being stored. Other thing was sparse enough or zero sparse. So because of this result we are trying to use it in a sense. This parameter space is nothing but number of hidden layers. For example, when we consider this is called the MNS. Like this is the famous data set. MNS dataset is nothing but where we have zeros and ones, we try to identify what digit it is. With respect to giving an input or output, we try to find identity. So when we do this is the data set, when you do operation on this, so these were the parameters. The channels are nothing but the convolution layers. We do the convolution and pooling method, like pooling is nothing but considering a particular kernel space and approximating it. So after doing this operation and making it, so this corresponds to the parameter space. Again, once again, this again will be the matrix. Like we could see only the diagonal elements are there, other are sparse. So that result we try to enrich and go about it. So moving on, we find MNS dataset. Like this is other thing. Like when we observe with another optimization algorithm which are present. When I guess this is. So when we check, when we go about SVD method is the blue line we could see observed here, whereas EPAC method what we observe like eigenvalue based here it's here. We could see how much the loss is very much less than the corresponding one. How efficient the methods are. Than the in today's world people use Adam optimization very much. So when you compare the Kronecker method, Kronecker is far better than the like Adam's one. So that's what we try to observe in this data set what we do after the coding part. We went to another data set also. This initially I told about MNS is identifying the digits, right? So but CIFAR data set also, CIFAR data set is nothing but a data set which contain airplane or everything. We'll have everything over here. Here also we observe the better results than any other thing. when the frequency of the the frequency of the search is higher, we could see how much it is far. The Kronecker method is much better than the present optimization method. So this was about the first applications.